Professor.
Okay. Bring myself on. Newton Euler equations for the top. Okay. Have pictures similar to what we had last time. Z, Y, X. These are inertial axes. That is Z axis. The angle about it is omega. Just a second. Somehow I don't like this one. Oh, yeah, well, let's consider that's the case. This is O. This distance is L. X, Y, Z are the body inertia axis. Here the M sub X equals to. This is the W, WL. Let me introduce this is the angle theta. Okay. WL sine theta. All right. And that's equals to I sub Z times omega times omega. That's precession speed. Now that's the proper rotation. Okay. This is the angle C, precession angle. So the omega precession equals to approximately WL sine theta over I sub Z times omega. Now the I sub X equals to I sub Y equals to I, right? Okay. So the body is spinning about fixed point O. Okay. And we will then have I don't think I did the axis correctly. So we'll have the theta is the nutation angle. C is precession angle. And the phi is the spin angle. About z axis. All right. Now, just like as before, write down that for the body, we have the omega y of the body equals to c dot sine theta. All right. That's the k, and the psi dot is the same direction. And we have this is That's the z-axis, and that's the y-axis, and that's the theta. So we project, that's going to be this. And then we write down that the MOX equals to d over dt of I matrix times omega. On the x-axis. And the I is, that's d over dt. Of the I, it has, there is the I in the x direction, I in the y direction, and IZ in the z direction, times omega. And omega has omega x, omega y, and omega z. And this is omega z plus b dot omega z equals to c dot cos theta. So this is the omega z that we talked about, plus phi dot, this proper rotation. So that will give us the I times omega x dot plus is going to be the omega as a vector cross product with I omega. All that times x on the x-axis, all right? Let's do this separately. So we'll have it there, right? We'll have it. Omega cross product with I multiplied by omega is equal to ijk omega x, omega y, omega z. And this will be I omega x, I omega y, I z omega z. So that will give us on the I-axis is going to be omega y, omega z, omega y, omega z times I z minus, so it's going to be omega y, omega z times I-z minus I. Plus j will be omega z omega x, omega z omega x is going to be I minus IZ, right? Omega this, yeah, omega z omega x times I minus IZ. And plus k, and that's going to be the omega x, omega y. And that's going to be the I minus I, which is going to be a 0, right? Okay. So going back to this one, the MOX equals to I omega x dot plus IZ omega y times omega z plus phi dot minus I omega y omega z, Well, the reason for this is this is the frame thing, right? Okay. The omega z plus phi dot, right? Okay. That's what happens there, right? Just a second, let me think about it for a second. Omega y, omega z. So, no, it's going to be this one, omega z plus phi dot. All right, that's the one. Okay. Y omega y times let me just correct this term a little bit. And that's going to be Iz times omega y omega z plus phi dot minus I omega y omega z. That's this term. The j's term minus, all right, so it's also going to be corrected a little bit. J's term is it's going to be this one, right? Okay. I omega x omega z minus Iz omega x omega z plus phi dot. Okay. And this one will be, and the third one will be, let me just erase this thing a little bit. Yeah, it's going to be 0, right? Okay. That's correct. Okay. So we have this one. Then we have MOY equals to I omega y dot plus I omega x omega z minus Iz omega x omega z plus phi dot. And we have MOZ equals to Iz times omega z dot plus phi double dot. Right? Now, about the omegas, we will have that in terms of the Euler angle, we have omega x equals to theta dot. Omega y we already wrote down. Will be c dot cos theta, c dot sine theta. We just check with sine. And omega z wrote down as c dot cos theta. I think that's what we did. Oh, it's the other way around, I think. Just a second, this one was cos theta. And this one was sine theta. Okay. All right, so this can be this one plus phi dot, right? So once we plug in into here, we'll have that MOX equals to I theta double dot minus c dot squared cos theta sine theta plus I sub z c dot sine theta c dot cos theta plus phi dot. Well, maybe this one is still cos theta. Let me look at the picture. Z will be c dot cos theta. So yes, so it's going to be cos theta here plus, sorry, this is cos, and this is sine. Cos theta, this is sine. So that's the first equation. MOY will be I m c double dot sine theta plus 2 c dot theta dot cos theta minus iz theta dot c cos theta plus phi dot. That's still the z piece. And now MOZ equals to I sub z phi double dot plus psi double dot cos theta minus psi dot theta dot sine theta. So these are the differential equation of motion, second order, nonlinear ODEs in theta, psi, and phi, right? Now I want to investigate precession. Steady precession. Steady precession means that the nutation angle equals to constant. That means theta equals to constant. So that means theta dot equals to theta double dot equals to 0. And then omega is equal to, that's the spin, equals to also a constant. All right. So spinning with a constant velocity. That means phi double dot is 0. We need to find, under these conditions, find c dot, the precession speed, which is equal to constant, and is equal to omega p. Of course, it has to be that c double dot has to be 0. So it's a constant precession speed. That means omega p dot is 0. So we have that MOX equals to WL sine theta. And we bring it in and we have in the equation 1, we'll have that WL sine theta equals to minus I omega p squared sine theta cos theta plus I sub z omega p squared sine theta cos theta, and plus I sub z omega p times omega, which is the phi dot, and times sine theta. That's the equation, all right? And the equations 2 and 3 give us that MOY equals to MOZ equals to 0. And that results in 0 being 0 for both equations. This first equation, we'll call it a star. And we'll see what we can fish out of that one. Out of the equation star, the first thing we can say, first case is sine theta is common and it's 0. So theta is 0. There is no precession. The top is vertical. That's of no interest to us. Once it's out there, we divide by sine theta. And so the equation will now be divide by sine theta. And we get that I minus IZ omega precession squared cos theta minus I sub z omega precession omega plus WL equals to 0. So if sine theta is not 0, then you'll get the following quadratic equation. Solve quadratic equation for omega p. So omega p turns out to have two values. Will be I sub z omega over 2 I minus I sub z cos theta, and plus or minus the square root of I sub z omega over 2 I minus I sub z cos theta squared. Subtract WL over I minus IZ cos theta. That happens when you divide this equation by I minus sub z, so it's going to be omega p squared minus omega p times omega I sub z over I minus I sub z cos theta, and plus WL over I minus I sub z cos theta equals to 0. From this one, we get this formula, and therefore we have two precession speeds. Omega P1 and omega P2. Now we'll investigate them. Their signs depend on this sign, right? Okay, the product of them is positive. Well, it's not positive. It depends on I minus IZ, all right? So if I minus I sub z is positive, means I is greater than I sub z, we have both of them, omega P1 and omega P2, are both positive. So both speeds are precession speeds in the positive direction. However, if I is less than I sub z, then we will have omega P1 and omega P2 of opposite signs. One positive, one negative. Now, the limiting case is what we got in the approximate analysis. The limiting case just a second. The limit case, what we got in approximate analysis at the very beginning, what we got in approximate analysis is when omega is much greater than omega p. So the proper spin is very fast compared to the precession. In that case, first term in this quadratic formula is much smaller than the other two. In that case, the I minus IZ omega p squared cos theta is much smaller than the I sub z omega p omega plus WL, all right? Because this is omega p is smaller than omega, right? So in that case, you will have that just a second. In that case, you have that omega p equals to WL over IZ omega. Always said that, call this one spin, all right? We'll do the stability analysis next time. Let's do some simple problems from the book. Maybe we'll do the, okay. Next time we'll do stability analysis of this one. At this point, let's just look at the book and see what problems they have to begin with, right? Okay. Book. Open the book. Page 228. Let's look at problem 4.7. Number 4.7. A homogeneous cube with sides of length A has XYZ coordinate system attached to the three intersecting edges, right? If the cube rotates with angular velocity omega equals to this, find the angular momentum about the origin and the kinetic energy. All right. That is the cube. Three intersecting angles. So that's the axis of the cube. Length A. And we can see the center of mass will have coordinates of A over 2, all three, right? Center of mass coordinates of x equals to A over 2, y equals to A over 2, and z equals to A over 2. You agree with that? Somewhere here, right? Okay. So we need to find the angle moment about the origin, all right? That means we need to find the O about the origin. So the H about the origin equals to the I about the origin multiplied by the omega vector, okay? I by the origin contains the following things. That's the, let's draw this, let me just remove this letter for the time being and draw this is going to be the vector from the origin to the center of mass. That's the vector D. We need this to find the products of inertia, right? So we'll have the I about all three axes will be the same, right? I will be I center of mass plus the mass times distance squared. Let's see, the mass of the cube is given, right? Sides A. Let's assume the mass is given, right? Okay, the mass is M. Plus mass times the D squared. And in order to get the XX, right, let's say this is XX, and we have this axis through center of mass is parallel to XX. So the projection will look like this. This is the center of mass, and this is the O, and this is the distance of one, all right? So plus MD1 squared, okay? IXX about center of mass, taken from the elementary textbook. Second. Okay. From the textbook, it is like this. See if we take a brick, elementary textbook. Okay. This is the G. Okay. This is distance B. This is distance A. This is the y-axis. Center, right? Okay. Hang on a second. This distance is L. Okay. So I G, that's GYY, is equal to 1/12 of mass times B squared plus L squared. In our case, we have B equals to L equals to A. So the moment of inertia about center of mass, IG about YY equals to IG about XX equals to IG about ZZ equals to 1/12 of M times A squared plus A squared. That's going to be ma squared over 6. That's about center of mass. Now we use parallel axis theorem. I x6 about O, the O being the origin, which is where the 3 ribs intersect. About O x6 will be, well, it's basically will be the same as I O y equals to I O z will be the ma squared over 6 plus m times d1 squared. Now what's the d1 squared? It's this distance, this length here, right? So d1 vector equals to d1 equals to a over 2, a over 2, a over 2. So d1 squared equals to a squared over 4 times 3, which is going to be 3/4 a squared, right? So the result is IG. Sorry, IO YY equals to IO XX that equals to IO ZZ equals to MA squared over 6 plus 3/4 of A squared times M. And that will be MA squared times 1/6 plus 3/4. This is times 2, this is times 3. This is going to be 11/12 ma squared. That's the 3 moments of inertia about the origin. Now the products of inertia. Due to symmetry, the products of inertia about the G are all 0. Ig xy equals to Ig xz equals to Ig yz equals to 0. All right. But IO about xy, for example, right, equals to Ig over xy plus d1 x d1 y times the m. Now d is the vector that is going from the origin to the center of mass. Therefore, it's going to be 0 plus, there's going to be d over two times d over 2 times m, and that's going to be m d squared, sorry, d over 2, a over 2. Because d is the d1 vector, it has components a over 2, a over 2, a over 2. It goes from where we want it, from O to the center of mass G. Okay? So O plus a over 2, a over 2 m, and that's going to be m a. It's going to be m a squared over 4. All right. So the result is that the inertia matrix about O is given by the following pieces. These will be 11/12 MA squared. So MA squared can be factored out. That's going to be 11/12, 11/12, 11/12. And these were all -1/4, -1/4, -1/4, -1/4, -1/4, -1/4. And now we can find the H. H about O equals to this matrix, which is MA squared, 11/12, 11/12, 11/12, -1/4, -1/4, -1/4, -1/4, -1/4, -1/4, multiplied by the vector of omega. And omega is 2 minus 4 and 3. He calls it L, I calls it H. 2 minus 4 and 3. Right? That's going to be MA squared. And here, let me use my calculator to figure out these quantities. So this will be 2 times 11/12 minus 1/4 times -4 minus 1/4 times 3. And this will be minus 1/4 times 2 plus 11/12 times -4 and minus 1/4 times 3. And the last one will be minus 1/4 times 2 minus 1/4 times -4 and plus 11/12 times 3. That's going to be the angular momentum. And that's equals to MA squared. Now let me now use the calculator to figure it out. Two times 11/12 plus 1 and minus 3 divided by 4. This will be 2.083 minus 0.5 plus here minus 0.5 minus 11 divided by 3 and minus 0.75. It's going to be minus 4.9917. And the last one will be 0.5 plus 1 plus 11 divided by 4. It's going to be 2.24. 2.24. That's the HO, or the way he calls it, LO, right? Okay. Angular momentum about O. Now, the next question is, find the kinetic energy as this thing is rotated about the origin, right? Okay. The kinetic energy is easily found. Kinetic energy rotating over about O is equal to 1/2 of omega rho vector, which is omega transpose, times the HO vector. It's going to be 1/2 of the omega is 2 minus 4, 3. And the HO has these components that we just evaluated. 2.083 minus 4.917 and 2.24. That's all multiplied by MA squared. Okay. The result will be 1/2 of, why does it do it? 2 times 2.083 minus 4 times minus 4.917 and plus 3 times 2.24. And there's going to be, let's not forget the MA squared. It's going to be the 15.28 MA squared. All right. Another problem down the line. Let's look at another problem. You guys have any questions about this problem? No? Can I go to the next page?
Yes, Professor. Thank you.
So the next one is problem number 413. Hang on a second. This. Yeah, let's try that. 413. No, that's too big. Let me try to shrink it a little. Horizontal shrinking achieved. Vertical shrinking is achieved. Almost. Okay. That's better. All right. You guys see it? That's problem number 413. A thin homogeneous disk of mass M, that's this one, and radius R spins at a constant rate omega 2, that's this one, about an axle held by a fork-ended horizontal rod that rotates at a constant rate omega 1. So the rod rotates about the x-axis, this one rotates about the z-axis, right? Determine the angular momentum of the disk about its mass center. That's too easy of a problem, right? Okay. Find the H G of the disk, all right? Well, we need to be able to write down that in this case, the omega vector consists of the following. It will be omega 1 plus omega 2. Omega 1 is omega 1 I, and omega 2 is plus omega 2 K. All right. Now, we just write it down that the H about G equals to the I about G times omega vector. So we need to write down what's the I about G. And that will go through the tables for the disk. And so let's write down, it's more explicitly a little bit. It's clear that these are principal axes. So it's going to be the IGX, IGY, IGZ. And the omega has omega 1, omega Z. Now, because it's a thin disk, let's see what it is. We'll use a cylinder. All right. From the tables, from elementary vector mechanics tables. Unfortunately, this book doesn't provide a table. Tables, we have the following. For a cylinder, of length L, this is its x-axis, this is the z-axis, and probably this one is the y-axis, and that will be the same, and we have the ix equals to iy equals to 1/4 of mr squared plus 1/12 of ml squared. And IZZ equals to 1/2 of mr squared. when you have a disk, the L goes to 0. So we have Ixx equals to Iyy. Just a second. This one. Okay. Equals to 1/4 of mr squared. And Izz equals to 1/2 of mr squared. So that means in our case, the Z is there, so we'll have that our I matrix about G is equal to XX is 1/4 of mr squared. YY is 1/4 of mr squared. And ZZ is 1/2 of mr squared. Okay, so therefore the H sub O equals to 1/4 of mr squared. And that's going to be 1, 1, and 2. Multiplied by the omegas, which is going to be omega 1, 0, omega 2. I believe so. Yeah. And that's going to be 1/4 of mr squared. And we'll have omega 1, 0. That's going to be 2 omega 2. That's 413. Let's do another problem. Do we have time for another problem? Well, let's try to go over time a little bit. Let's see. This is a good one. That's 14. At least we'll start it, right? Number 415, 415. Number 415. I'm going to draw a sort of a increased picture like this. So that's a wheel. And we have let me just copy it. L, A, and omega. So this is the omega. This is the O. This is L. This is A. Here is a deal. Oops. This says this is velocity of, this is A, this is B. Velocity of B equals to 0. Velocity of O equals to 0. Therefore, OB is the instant axis of rotation. Okay. And therefore, it's parallel to resultant omega. So we have, this is the omega that we're given. And this is the omega of the disk that we need to find out. And that's the omega resultant. And this is A and this is L. So we can say that's omega disk to omega, that's this one to this one, is like L to A. So the omega disk equals to omega times L over A. All right. We have these two. Now, we needed to find the did I copy this thing? Just a second, let me see. Oops. Yeah, let me try to reduce it. Oh, more narrow. Okay, almost there. Okay. There's going to be the omega is this one, that's the omega. This is going to be 2. L is 50. A is 10. It's going to be 10 radian per second, right? Okay. Find the energy, kinetic energy. All right. And the kinetic energy will be T equals to the I matrix about O times the resultant omega. That's I about O, sorry, 1/2 of omega times this. So hang on a second. Let me just correct it a little. It's going to be 1/2 of omega transpose times I about O times omega. Okay. All right, the omega equals to omega x, omega y, and omega z. Look at the picture. Right there. Let's call this one to be the x. This is to be y, and there's going to be z, right? Omega z equals to that omega that is given, and the omega x will be minus this. It's going to be minus 10, 0, and that's going to be 2 that is given. All right. Now I about O equals to I of x equals to, it's just going to be disk. It's going to be 1/2 of mi squared. It's going to be 1/2 of m, and the mass is 0.25 kilograms. And the A is 10 centimeters, so that's going to be 0.1 squared. It's going to be 1.25 times 10 to the minus 3 kilogram meter squared. Okay. I of y, we don't need the y, we just need the z. I of z equals to, it's going to be 1/4 of it, and then plus ml squared. It's going to be 1/4 of m a squared plus ml squared. M times a squared over 4 plus L squared. The M is 0.25. The A is 0.1 squared over 4. And the L is, I believe, 50 centimeters. That's 0.5 squared. It's going to be 63.125, 10 to the minus 3 kilogram meter squared. All right. And then we'll have that the energy T equals to 1/2 of, and there's going to be summation of omega I squared I, and we have just 2 pieces. omega x is minus 10 squared, and the ix is 1.25 times 10 to the minus 3. And plus the omega squared times 63.125 times 10 to the minus 3. It's going to be 0.189 kilogram, sorry, joules. Right? Kinetic energy is in joules, all right? The other question here in this problem is find the reaction at pivot point O. That's right there, okay? And the normal force exerted by the ground on the wheel. All right, let's do the free body diagram. The reaction, let's see, what does it say? Pivot point O. Wheel. The wheel is rotating like this. So the wheel is rotating like this. All right. So this point is moving here. All right. And that's the direction of the force, that is friction force that is putting it, that is making it rotate. That's the F at point A, I guess, right? What's the point there? Yeah, F of point B. And we have three components of the force here. It's going to be F of Z. Let's see, what are the components of there? The F of Y and F of X. Right away, we'll discard the F of Z because the force F of Z is absorbed by the axle here, right? Okay, so that's not the way. So we just discard this. We'll just handle the F of X, F of Y, and the FB. All right. So we'll have the following. There is no translational motion, so that means forces by themselves will not be of interest to that, but rotational motion is there, right? Okay. Mostly F of Y, right? So we'll have the let's start with FB. This is O. Okay, and this is x-axis. So we have the moment about x-axis equals to, the omega is constant. So therefore, looking at the equations, let me just remind you there. We have that omega x, omega y, omega z. We have the cross product with I omega x, I omega y, and I z omega z. We do the cross product, and that's going to be, let's do the ijk, omega x, omega y, omega z. And that's going to be I omega x, I omega y, sorry, I x omega x, I y omega y, I x omega x, I y omega y, I z omega z. We do this, we'll have the I times omega y, omega z times iz minus iy plus j, and that's going to be the omega x, omega z times ix minus iz, and plus k is going to be omega x, omega y times iy minus ix. These are the components that will have to go into there, into the MOX. MOX equals to omega y, omega z times iz minus iy. All right, that's where it comes from. The MOX equals to the friction force times L. Okay. And it's going to be rotating about x-axis in the same direction, right? Okay, equals to the omega y, which we have as 0. No, that's not right. Okay, omega y, omega z. Just a second. Let's see. I guess so. That's right. Yeah, there'll be. So FB y, and this is going to be FBX, FBZ, right? Okay. A bit can be right. Just a second. Let's see. We have a moment about this point. Okay, moment about this one. Omega y is 0. Omega z is not 0. I guess that's what it is, right? Omega z minus omega y. But omega y is 0, right? So MOX should be 0. That means FBY is 0. But there is another component here. Probably. Tell you what, we'll finish it next time. We're already in the overtime mode anyhow. All right. See you guys next time.
Thank you, Professor.
You're welcome.